Welcome to High Performance Computing, Advanced Scientific Computing. This is Practical Lecture 1.1 and the second part of it. So the first part was introducing us a little bit to C programming on HPC systems. So admittedly, that was a very short introduction to C because essentially we had a very little program called Hello World. And we learned to include a small header, standard IO, and do a printf statement and return a 0, saying it was a good execution. Hence, one of the most, let's say, smallest probably you can get in terms of an C program, but it captured the essence of compiling it first before you can do anything with it. And when we do this on HPC systems, we need HPC system software for it. Hence, there needs to be installed compilers, or the MPI environment, the libraries needs to be installed. And we learned, for instance, in our example, we used OpenMP i4, an implementation of the standard of the MPI interface and library. So it's called the message passing interface. It's a basically standard in HPC that covers almost all HPC systems today. So chances are, if you take one MPI program and compile it, work with it, do research with it on system A, then you basically can use the source code MPI. You maybe have to recompile for the environment there, but still the program would run on a different HPC system because the message passing interface is really a standard as well as C. Hence, this was the first step towards going to an MPI program that will, come in later lectures. We will start with lecture 2, then MPI later, and then do a practical lecture 2.1, where we then enhance essentially the C program that you have seen to a proper parallel program with MPI statements. But before we do so, we learned a little bit at the end of the first part that executing and then a C program which has been properly compiled, that is really ready to run, is it not good to do this on a so-called login node. And hence, starting this practical lecture here in the second part means we should go a little bit back to the descriptions of the systems because we want to use ELIA. So let's do this a bit. For instance, you remember in one of the lectures I told you there's a user documentation where you essentially have a description what's happening on ELIA, right? So this is all about the environment, what you do there. You have some specifications of the hardware here in different parts of the system and with different, let's say, vendor elements here. For instance, you see here an A100 card from NVIDIA and so forth. But quickly, when you do so and look at the idea what essentially ELIA can do and what idea of partitions they are to use, which has different partitions, and UTUN is, for instance, one of them that we're going to use for our, let's say, teaching adventures, then it is important to understand that everything is always giving you an indicator. There's a slurm, right? The submitting batch jobs idea, which you see also here, for instance, explained similarly, like I will do a little bit today, but of course here you have a bit more elaborate discussion, what you can do, and information should be always available, on the web for these systems usually. Hence, what we do here now is relevant also for other systems, such as those in Jülich, for example. Hence, let's go a little bit into the example here, just to understand now why also these systems are so much a multi-user environment, right? So here we have the idea how we in Jülich created the systems since 2004, and it's a little bit outdated maybe, but was growing through the, let's say, generations here, and you see 2015, 2017, all EVM systems, quite a lot actually, which are now not anymore in action. The same with Jewels and Jewel Scalable. These new modules, all based on this modular supercomputing power and idea that we, let's say, have already explored a little bit in the last lectures. Hence, the modular supercomputer architecture idea is really serving the needs of different users. And this is now the key point. Obviously, these systems are not like your laptop, right? You're not alone on them at the same time. There are many, many different users. And on top of this, these different users want to use the supercomputers differently. They have different needs, and here you see quite nicely figured out essentially two needs. On the left-hand side, the Jewels cluster is a module which has high single thread performance CPUs, number crunchers, like we have seen with lots of multi-core chips. And then you have the Jewels scalable module, which is named as a Jewels booster these days, which essentially means highly scalable codes and modules, and also lots of many core chips available, GPUs, right? So hence, the applications that these different users do at the same time on the Jewels cluster, on the Jewels scalable system, the booster, is essentially different applications with different needs. Hence, this modular supercomputing architecture has been created for this. And the reason is that, of course, not every user can have his own big supercomputer, right? We share these big systems with many, many different users. And to give an indicator how many we're talking about, I show you a little bit here a command and control center, if you want, from the Jülich supercomputing center. You see a little bit here also the hall, but this is not so important. There's a hall with big computers you have already seen in the last lecture. Here we're talking about so-called monitoring systems that show the load on these systems. Here we see LLView, right? This is a historic system grown in Jülich, but can be also used in different HPC systems. Hence, you can see a little bit with this wide variety of colors here, and the details for you are not so important to understand, but all the different colors stands for different jobs or activities, tasks, applications that, all different users have, run or running now on these different systems. Here's an examples of the Eureka cluster, for instance, or the Eureka booster, again, modular supercomputer, different needs. And then also the Jewels system, for instance. And you clearly see with all the different colors here that there are many different jobs at the same time now running on these large supercomputers, right? So this hence means we have to have a system that not only showing this, like the monitoring system now, this is beautiful because this enables us to understand what's happening on the system. The other point is we have to make sure that they can actually run jobs at the same time, that there's capacity, for instance, that there's enough, let's say, room for these applications. Because if everybody can submit every time their jobs and say, please run now, chances are that at the same time, there's not so much capacity available, right? Especially if you talk about, cutting edge deep learning algorithms, what we do here. Because what you quickly understand when we go into later lectures also is that we not stay with one node, right? Or with one, let's say, GPU. Here you see we want to have more GPUs. That usually brings us then to the different blocks here. So we don't want to have just one node, we want to have more nodes. And with this, you can see already that the colors are not in one small box, but rather bigger blocks, like here, the Jewels, or nicely seeing, you see this also in the Eureka booster here with the jobs spanning quite a lot of the fractions of the whole system. But to order to, let's say, manage this load, right, for users, that's an important part. And that brings us to what we call then the scheduling system. So this enables us then really to, let's say, run different jobs at the same time, while each of these jobs are run in parallel also, right? You would say, of course, they are all run in parallel, but each of the applications has then this parallel programming inside that also executes in parallel. So a bit more detailed view as an example, and that this is Jewels and not Elia doesn't make a big difference. So Jewels essentially says here that, there's a so-called job list here. You see that here. Many different users have here now submitted a job, and we will submit a job to Elia so that you understand a bit what that means, and using scheduling. And this is basically what's happening right now in the system. And you have here a timeline also below. You will see, okay, it's quite filled. And you see that as a normal HPC system production element. So especially in the large system, which costs a lot of money, this system should be used. Hence, you will find the utilization, which is almost 99% in many cases, right? Because also these systems are needed by researchers and required. They are often oversubscribed even. In order to get access, usually you also have to write computing time grant proposals, and these are granted or not granted depending on your scientific excellence, on the task you want to do, on the application. So in a way, these systems are usually cost-free if you are in academics, if you are basically in the scientific and engineering fields, which are more or less in research. Of course, you have similar aspects in clouds. Some of you know that from my cloud computing course, but these are usually not these big systems that we have, for instance, in the EuroHPC joint undertaking and so on. So the concepts, however, are all the same. So all the EuroHPC systems I was showing you already, Leonardo, Mare Nostrum, Lumi in the north. So this is all multi-user systems. Very many systems uses different modules in these systems for different applications. And we have usually two of these elements, monitoring systems that show you a little bit what the load is, and then also the scheduling system, which is very essential to make so-called batch processing. And the batch processing is a bit good to understand when you think here about the batch queues. What you see here is that someone has already submitted different jobs for the future work, right? So, or some basically here will be started because they submitted at some point in time and it's already scheduled basically here in the timelines of different processes. And with this, you see that, of course, the batch is, so to speak, a kind of queuing mechanism of, letting the people submit their needs on the HPC systems, how many nodes you need. And depending on the space, you can get basically scheduled in a certain amount of time. In other words, it's not really always interactive access, right? So this is sort of the difference between batch systems, where you have a batch queue waiting for you, and we will see the queue later when we use it, and also, of course, in lecture 2.1 and so on throughout the course in your assignments. You will see that there's quite many systems in that, many users in these queues, and this is an important factor of it. And the name of these could be very many. So some call them computational jobs. Some call them batch jobs. You will see more and more people working in HPC, they just say jobs or tasks. Nowadays, we say AI tasks or AI load, from the load of the machine, from the amount of AI algorithms, applications running from different users. So there are different names for similar elements, but all have in common that they use a scheduler usually for some purpose. Now there is a sort of bypass called Jupyter Notebooks, which we also explore later in the course, which enables you interactive access, but is a different element from just doing this batch submission that we see here now. Hence, we turn our, let's say, perspective to the Jupyter Notebooks rather when we do deep learning from lecture 6 on. So at the moment we stay with the batch submission as the one that is basically used also for highly scalable aspects. So hence this LLView tool hopefully enables you to better understand that these are all different jobs, different users at the same time executing on these large systems. You see a full hall of computers used by different ones, and that we also, of course, want to have the load quite, high, like 99% would be ideal, of course. Some of them don't have that, like our university systems is maybe sometimes only 20%, because this is also not, let's say, a costly system like Jewels here, right? It's a smaller systems, not so much research done there on the one hand, and also partly used for teaching, and a complete different, let's say, order of magnitudes than these supercomputers that we have seen, for instance, in EuroHPC, in the joint undertaking with Mare Nostrum, Leonardo, Lumi, and so on. And this will be also the case for the Jupyter HPC system, the first exascale system coming up, where we also talk later in the course about more. All of them will be still using scheduling, and hence we want to understand a little bit more of it. Just to summarize what I said, you have this different monitoring systems that you already know now. LLView was one. I also have this ganglia on ELIA here. I will not make a big tour on this, just that you know that we have here in Iceland this Ganglia system, for instance, to understand the load, what is happening, for instance, in the last hours. You see hour, 2 hours, 4 hours, and you see here different, CPUs, the nodes, the what is running there really, the peaks and so on and so on. So you can see a little bit what's happening in these systems. You can search a lot, can tune a lot, and I don't want to make it Ganglia tutorial out of this. So you see also this is maybe quite interesting. We said a little bit the current load average was around 20%, as I was mentioning. In normal supercomputing centers where you have really large production machines for huge research projects, there would be rather a load of 98 or 99%, because these are very expensive systems. Here we're talking more about a smaller, let's say, regional system, and with this I think the load is okay. And there are many other systems. As I said, LLView could be also here, and can be something maybe installed in the future on Elia. But it helps you to understand, also other elements that we didn't talk much about it. One example is, for instance, broken nodes, right? Sometimes could be that, CPUs overheat and they have to exchange the node cards, whatever. So the network is down. So you sometimes have also the system health checks, and the information is basically all the nodes and all the node cards in the node really active. That means essentially when you come back to one of these, that sometimes some of these might be, empty, and the reason might be, for instance, maintenance, or you see very clearly that there's a, X, or that this particular node is broken. So enables you not only the load, but also the system, view and monitoring, which enables us to see this kind of errors in hardware as well. Coming now to the scheduling system, what this lecture is primarily about, although monitoring, you have a sort of view that this, of course, is quite related, right? Monitoring systems often show the schedule or the batch queue or the users that are using the batch queues. Hence, these are managing really the concurrent access of the users of the computers, and we want to do it here a little bit in practice. So we would go a little bit also to the idea now of submitting Hello World on these systems. For this, I would start maybe just practically by logging in to Elia. And by now, I mean, this is something what you basically should know by heart now, right? We need the host name. We need to specify a certain username that you have. And of course, we use a private key to get access. And my public key is already uploaded. And voila. The usual wait a bit before we log in. We use that to explain a little bit the different commands that you see here, which is then now the scheduling script. So there is another file that goes along the specific job that you have. Let's say you have a Python, file with some Python code you want to execute, but it doesn't really matter. It could be also a C program. The point is that your top of the file from the so-called batch script has some certain information which needs to be filled and is basically informing the scheduler of what you need. And here's a good example. We have one node and we want to have 48 cores per node. And it depends now on the system, what type of cores we have, dual cores, etc. So you have to look around exactly what the hardware architecture is in this. Hence, these kind of overviews, for instance, partition utun, if you remember, comes now to the point that you always need to understand a little bit on the architecture of the HPC systems, right? So different partitions and so on. And this also sets it a bit apart from some of you that know my cloud course, right? Which is a bit easier. You don't need to have this low-level details, rather, create just one cloud service, executing it, maybe knowing a little bit what you want to buy in terms of GPU type or CPU type for different costs. But here you have different specifications, and you see here the partitions that are available on utun, which is for us for teaching. And you have here in the 4 Newton computing nodes, which have then, let's say, 2 times 24 in each, cores per node, and then the different memory, what type of vendor, and so on. And also a GPU is available, an A100 from Tesla. So with this information, then there's a partition available for us in teaching, and it's also for you in the assignments important to understand that. Please stick to it, because we also have your, let's say, your usernames are ready for this particular partition and not for others. You have the number of nodes, the number of tasks per nodes. You can also request for different memory. Then we have a so-called time that we want to have for a certain amount of running time before the job gets against the wall. This is things I will also explain you later a little bit in the course. You cannot press everything here inside this one. And then a little bit on output and error, which I also want to directly show you when we come essentially to the practical example. And when you submit these so-called job script, because it describes the job you do, the scheduler will handle this, will read this, and then also be able to schedule your job according to your requirements at the point of time where the requirements are fulfilled. It could be also that you request something which is not doable, right? Let's say your overall system has just, that's 100 nodes, but you require 120 nodes for your job, then you should be rather going to another system, because Sloan will know that 120 nodes are not there. So hence, again, you need to consult the description of the different respective resources, and to understand also what type of jobs are used in which partitions, especially if you think about the modular supercomputing architecture again, right? If you want to have a couple of CPUs just used for a small MPI run with 4 CPUs, but submitted to a large booster, which is usually starting with maybe jobs starting with 512 or even 1024 CPUs, that's an important part. Hence, we talk about here something which you really need to consult in, let's say, collaboration with the administrators, which often give you really a page like this. You will find a similar page, for instance, in the Jülich Supercomputing Center for all the different HPC resources, if you remember from the last time, Eureka, Jewels, and so on. And here is our system Elia, and it also describes the partition information, but it gives you also the idea of how to submit batch scripts, how to basically have the commands here that I will demonstrate now a little bit. And again, of course, connecting SSH was something we know before. Also software that we have seen a little bit with the module environment, right? Here you see software for different, areas of sciences, VAS, for instance, in chemistry, and so on. So this is what the people are using in different areas of science. Even AlphaFold is quite interesting because it's an AI tool that was recently created and used. If you know, basically this is quite some interesting set of software and information, and you need to use this usually when you go to another, let's say, HPC system. You will inform yourself a little bit about the architecture and the partitions and so on. How the jobs are scheduled is sort of a huge scheduling theory. There are lots of different algorithms how to do scheduling, and it's a whole research area actually where people publish in. One of the most used is maybe first come, first serve, where then also a certain technique called backfilling is applied. So let's say, as the name suggests, you have submitted a job early. That means you're somewhere in the queue, and then you should be also handled earlier than others is submitted after you. However, if your job specifics will find a gap that fits to the number of CPUs or GPUs or memory what you need, and it's maybe, let's say, too little for the other one, for all the others that submitted maybe before you and still wait, it can be taken in front, right? Backfilled. So in this sense, the gaps should be filled when there's free computing capacity. Good, but let's come to some practical examples. So in the remaining part, I also here now on Elia logged in as usual. I not will explain how I did this. I think by now you get the heck of it. We go to our directory that we had already created, if you remember, MPI, and then our beautiful hello, simple idea. For some fun, we remove the hello again, and we remember, right, we have to do the module avail from the last part. We see, okay, now we have an MPI OpenMP implementation. That's nice, it's convenient, I want to know that. Module spiders, just to repeat a bit from the last time, I see no dependency, so I can just beautiful module load this here, right click, fantastic, have this, and then I do this MPICC -O for hello with the hello C source code. Just repeating a bit, having the executable. But we have also learned, and this was the stop of the last part, that this is not the way to do, right? The reason is now that we are on the login node. Right, and this is something which is not good. And we have some hostname information, name that we are essentially on one of the systems on area. That is good, but you see also clearly we are on a so-called login node here, which is not the way to really execute. Now, when you execute hello world, no one is hurt, right? But if you execute now a climate simulation with lots of computing power that goes into it, chances will fail anyway if you start, because you have not a round of memory in the login node and so on and so on. But basically running on the login node, that's a no. Compiling, let's say sometimes even doing smaller modifications to the code and then compiling longer parallel compiling and so on will be then rather done on the compute nodes. Parallel execution would be done on the compute nodes, because there parallel computing is possible. Right here, the login node is really a node just for compiling smaller elements, like we have here now with the Hello C program. And hence this brings us to the scheduler, right? If you remember, this was the one important element of the graphic that you see here. We want to use now the scheduler in order to come to the compute nodes, right? And I come to all of this, which is here on the slide. It's a complicated slide, but we will get the message when I go into the example. And the slide before just basically shows the submit hello idea. So hence, here's a job script already. We go into it. It's prepared. It looks a bit simpler, what you have seen on the other, let's say, slide in the presentation, where we have much more options. Here we keep it to the necessary ones in the beginning. So we have a job name. We say it's an hello example. You know that we have to specify the partition utin as part of our teaching cluster. Then we specify for the simple, trivial hello world, indeed, just a one node, and then even, of course, one task per node is also one, to make it very simple. We will change that later, and when we have MPI and so on, we will use, of course, more tasks per node, and then maybe even more nodes. That's important. But then other elements here are just my username. This enables us to get information if the job is done. For instance, if you say mail type end, then you always get a confirmation that the job is done. Now for this, let's say, small running hello world, we sort of expect an execution of the job which is very fast. So this is so not really needed here, but of course you get the message when you have, let's say, a 24-hour run of your climate simulation somewhere on the server, and you don't know really when it starts because it's queued. So you go happily shopping, you go sleeping, and in the morning you get an email and saying, hey, your job was actually run, it's finished at 3 o'clock in the morning. Congratulations. Then you're happy of having this kind of notification. Hence, many of the aspects we teach here in the small scenario we do for teaching, it probably doesn't make sense. But this is a way how you would do it also for proper scientific applications, for large applications that really require HPC. Now, another aspect of the job script is the right module environment. If you remember, we have load the module, and that's why I wanted to demonstrate this again, right? I'm talking about that we have been on this host name here, which is our login node, and we did here before module load. So that is now that this login in our session, the login node has now this module, but if screen into a file, and we want to look into this file, and this file is no big surprise, I guess. Everybody of you can already, I think, expect what's inside. Hello world. Now, this is not so obvious. It could be also errors, right? Let's say that the C program may be compiled, but during runtime, it misses some inputs, for instance, an input file or so, could be so some errors. And we will do this later when MPI comes along. Then we will do some other examples and demonstrators. And also in your assignments, it could be very well that you also get some error messages out of it. So here we keep it simple. You have seen that now how it works with this job script. Again, many of the things usually are also really nicely described by the administrators on the system, right? You have the S batch here. For instance, we have the SQ information showing the queue status. That is maybe quite interesting as well to do briefly. So SQ, who is running which jobs and so on. And of course, our jobs are so small that they're not visible. Here you see the whole system, you know, who is running on the different nodes and so on, and different usernames. So you can understand a little bit, you know, who is really using the system. But you see also from this SQ information that somehow it's not so intuitive like the monitoring system, but of course gives you quite details, right? So while the monitor systems was more an aggregated statistics view or so, if you want. So because later in this, we will also have some sleep jobs where we then also will see how we later will use the HPC queues and so on. We'll see our own jobs and so on. We don't do this today because it would be just a very simple way how to execute C programs. Of course, here and there, you can also get more information about the jobs. It's quite useful. You see here S control show job ID, for instance, S control show job ID, so job ID, and here you essentially have different levels of outcome with minus DD. And this is not forever. So once you finish the job, you have to be, let's say, relatively quick of getting more information. And here you see now more information and that, you know, the job is completed, for instance, that's important, which partition it is using. And for us now to understand the difference again to the sort of login node, we see here now clearly it was running on a node called compute 1. Right, and as I told you, Utun has compute 1, 2, 3, etc. So this is an important part to use. Really, it has used one task, automatically 2 CPUs because of a dual core, and we just stayed on one node. So this is something which you know, changes dramatically with the job script. Now, when you do, for instance, 10 nodes, obviously here would be a long node list with 10 nodes, or you know, also the amount of CPUs allocated and so on. So obviously this job script steers a lot what's happening in your job, and you can always control this a little bit here and check what's happening with this S control job ID. However, often we of course also just want to get the output, what we have done here. Also, if you use, for instance, you know, another output, there's no surprises, right? Hello world. This is something. Another element I wanted to show briefly before we close is if we remove hello now, just to understand again C in combination now with all of this, and you know, we'll do hello world, and we'll do, I don't have slides on this, but I think that's clear for you. Hello world 2. Now we change this in any way. You know, then we have to also recompile it again. So as we have already run essentially the kind of, you know, the module load, this is all easy. So we do hello and hello C again. And I don't need to change the job script in any way because, you know, this is now hello still there. So let's say with the same job script, I just say submit hello. And now with a new job coming out of this, when we more, let's say, well, let's make it more simpler. We say NSMSL, and this one is now having an out. You see already it's a slightly bigger, very tiny bigger, so to speak. But in this sense, we have Slurm showing us now, of course, hello world 2. On the other hand, of course, what's also important to understand now, if we have the hello C program, and if I turn this into a 3 and say now we have changed it for the 3rd time, but I sort of forget now here intentionally to compile, my source code is in the version 3, but the executable is in version 2. Hence, when I now SBatch it, there's no other choice than it will be the same output. And I think that's should be obvious to everyone. You know, when we do this now, the last submit was 21 here at the end. This is very clear that this stays on 2, right? Because we didn't compile it. And this is an error sometimes happening to developers in HPC that, of course, they change the source code and then they somehow get distracted and forgot about the compilation. Or basically the compilation failed even, and they thought it was going through and so on. There are many facets to it. Hence the naming, and later on also in versions and so on, is a big scheme and should be also properly done so that you always, let's say, have a good understanding that the source code that you have there is also like the kind of executable you have there. Hence, I will change this back in this simple demonstration now to hello world 2, just to be sure that we know, okay, this is the same. And in a way, that's all I wanted to leave you on the table today. Obviously, just a very short introduction to C and a very short introduction to Slurm job scripts, but it carries the essence how you do bigger jobs, how we will integrate MPI once you understand what MPI is, and that we have used now finally the MPI the HPC system as we should do, right? We're using the compute node to compute the hello world, even if it's not very time consuming, but this is how it should be done. And I just use the login node for compiling and submitting the job to the scheduler, what we have done. And this is a learning outcome, hopefully, for all of you understanding this different batch procedure in terms of how we execute on HPC. We continue tomorrow then with our lecture 2 on MPI, and then come back to practical lectures later on. So talk to you next time.